Well, good morning, everybody. We're almost lunchtime, and I hope you can still bear with me for the next 2.5 hours. Oh, sorry, 1.5 hours. Introducing you to the concept of quantum impurities and the Kondo effect. In fact, this will be the first of a series. There will be another lecture on Wednesday by me, which is then a true blackboard lecture, as Antoine's was today, on a very simple but for first crude shot quite powerful impurity solver, which is called non-crossing approximation. And behind that is a certain theory which is quite interesting, also in what Antoine told about the changes in states as a function of time on the impurity today, and also what Philip Werner will introduce to you as the so-called hybridization expansion quantum Monte Carlo method. Okay, I thought I don't want to really do a blackboard talk because, first of all, my handwriting is extremely awkward, so you rather want me to do a presentation. But on the other hand, the concepts I want to introduce to you today are mostly well established, well known, and one can do a lot with figures and drawings, so it's much harder to do on the blackboard, especially since I'm not very good at drawing anyway. So there's also very good literature on these aspects of physics I'm going to tell you. That's the book by Alex Hewson, The Kondo Effect of Fermions, which is, well, 20 years old now, but still, if you want to learn about the basic concepts of all the things we are talking about here, it's a wonderful thing to start with. Contains all most of the interesting techniques to solve these models, and for that you can also read it as an introduction into several tools. So the first part will be the introduction to quantum impurities and the Kondo effect. We've heard already a little bit about, or lots about, the mapping of the Hubbard model, or quite generally correlated lattice models, onto the impurity Anderson model. And the impurity Anderson model is a certain aspect of a more general class of objects called quantum impurity models. So what are quantum impurities? Well, from the very basic definition, you would say a quantum impurity is a collection of a discrete set of quantum states coupled to a continuum of non-interacting degrees of freedom. So the non-interacting here is quite important, otherwise you're lost. You're lost anyway, but then you would be even more lost. And the latter, those non-interacting degrees of freedom, can be either phonons or can be bosons. Sorry, fermions or bosons. Or they can actually be both. That's the most complicated situation you can have. And that's the one that might become interesting in the context of what Antoine referred to. If you want to include longer range bosonic modes into your fermionic DMFT, that's the extended DMFT, you actually need a combination of those both things. And yeah. Well, so that's the working definition. And let's start with a very simple but important example. And let us consider, as the collection of discrete quantum states, let us consider a quantum spin 1/2. Now this has two states, spin up and spin down, but of course you have these operators that communicate between those two, so this is a real quantum object. And let's couple them to fermions. So that's the picture I would like to draw for that. You have here your spin sitting somewhere with a spin 1/2. And there is a band electron system, which I very coarsely describe as a box which can be filled to some level EF, that's the Fermi energy. Of course, the electrons, band electrons, are also fermions, so they do carry a spin 2. And if there are two spins around, you know, there can also be an exchange interaction between the two. I don't care where that comes from presently. I just say there can be one, and we talk about later where it might come from. And this can make those two guys talk to each other, and this arrow should actually be up there. This is for the ones who like pictures. For the ones who like Hamiltonians, that's the Kondo model. I hope you can read it. It's given by a set of band electron states, which I call C, typically. They have a dispersion, which I call epsilon k. I don't care at the moment what kind of dispersion that is, where it comes from. I just know it has to be there. And then there is this localized spin S, which I represent by one operator. And then, of course, the band electron spin can be represented in a standard way using the Pauli matrices, sigma, which is a vector of sigma x, sigma y, sigma z. They have indices alpha, beta, which denote those 4 components. And then you have the band electrons from scattering from a wave vector k and spin quantum number alpha into a wave vector k prime and spin quantum number beta by virtues of this Pauli matrix vector. And this is multiplied into the spin vector. So that's a very standard representation. I hope you have seen already that you can represent a spin 1/2 by those combination of Pauli matrices and fermionic operators. And here we assume that everything is local, so the k and k prime sums are independent. You can become a bit more sophisticated and add a jkk prime here, but that doesn't really change things. Makes just life more complicated and formulas more complicated. So that's the Kondo model. Very simple model. Actually has been introduced by Zehner in a quite different context in terms of an SD exchange model, where D now refers to the D states. And for example, you could consider lanthanum manganite, which is a very famous system showing when doped colosmic resistance. They typically have T2G states and EG states. You have to accommodate 4 electrons in lanthanum manganite, for example, 4 electrons into the EG and T2G states. And Hund's rule tells you that you have to do it sequentially. So you have to put 1 electron will spin up in T2G, the second will spin up into the second T2G, the third will spin up into the third T2G. That's Hund's rule, maximize the spin. And that means you have a T2G half filled with spin 3/2. Plus the next one has to go into the EG and that will then sit over there. And Hund's coupling between the EG and the T2G is ferromagnetic. So what you could do is say the T2G is inert, doesn't do anything, but we have Hund's exchange between the EG and the T2G. The EG may move around, and you have this model, and you also now know where the J comes from, namely Hund's coupling would be ferromagnetic. So this is a more general model. It just tells you have a spin sitting there. It can interact by an exchange interaction, and don't specify the sign right now. Okay, fine. Okay, sometimes these gimmicks are a little bit... So why are these objects important? Well, there are tons of experiments these days. For example, molecules contacted to metals. So this is a more less artist point of view, where you have some kind of molecule sitting between, here for example, I think it's gold electrodes, and you try to contact this. And of course, such an atom is a set of molecule is a set of discrete states with more or less large gaps in between. And if you do it correctly and cook down your stuff properly, then you might be able to represent this by a spin. No, it must not be a spin 1/2. It can be something more complicated, but it can be possibly represented by a spin. And then you have this model, which I just talked about, realized in this type of setup. And what you can then study is transport through this model in the presence of the correlations on the orbital here. Okay, so that's one thing that is very modern, actually. The second, Antoine also talked about, is if you have electrons sitting in artificial atoms or molecules. These things are called quantum dots. And what they typically do is you take systems consisting of gallium arsenide and gallium aluminium arsenide. There's a slight mismatch in the band, and you get, by Poisson equation and everything, you get a small triangular potential dip at the interface between those two things. And this interface, in this thing, there are bound states. And these are truly two-dimensional bound states with extremely high mobility. And you know all of these things because every MOSFET uses that. And this is everything that sits in your electronic devices here. Now, you can play around with these things nowadays. You can handle them very nicely, nanotechnology. And what's shown here in gray are different, Antoine talked about these electrodes put on top of this device. And by properly tuning the voltages at the electrodes, you can actually single out the small dot here, which is the quantum dot. And this is something people have been suggesting by adding one larger dot here and produce a more complex impurity model. But not, what it boils down to is that you basically have a spin sitting on this dot. And the spin can communicate with its environment, and you can actually tune this communication. If you do the tuning correctly, then again you end up with a Kondo model, or as we already know, the more general implementation, the single impurity Anderson model. And last but not least, you can there's also two-level system connected to a Heath bath. In that case, here you always have the bath consisting of fermions. Sorry. In that case, the bath would consist, for example, of phonons. So a two-level system connected to phonons, or a two-level system connected to photons, or something of that sort, is also a quantum impurity problem in that sense. There are some possible realizations in two-level systems in glasses or artificial glasses, which show quite nice properties. And finally, and that's the old, yes? Wait a second. Yes?
We have a system where it's coupled to the bath, which is larger than, because you have a full-fledged bath of the free fermions, which is coupled to the impurity. So usually the coupling to the bath leads to the dissipation. So does that dissipation manifest somewhere in this quantum physics?
Dissipation, actually, yes, it does. It's in the bath. So basically, the bath is infinite, so it can lead to dissipative effects. That's the hope.
Oh.
And you can show it for certain special regimes. You can show that there is dissipation and a relaxation to a thermodynamic limit. If you switch on, do this kind of quenching. That's what Philipp Werner talked about. So the bath, if it's really infinite, then it can actually act as a heat bath or as a thermalization.
Okay, yeah, thanks.
Right. I mean, this is also something, if you do transport through these objects, this is a non-equilibrium measurement, and you have to worry about possible that you really have a thermalization so that you get a steady state or whatever. But that's nothing we want to worry about today. You can ask Philip about that. Okay, so then there's this very ancient, if I want to say, realization of quantum impurities, namely this is magnetic impurities in metals. And that's where the famous Kondo effect comes from. Now, I didn't find a nice picture showing an impurity in a metal. This is hard to get. But what people can do nowadays is put impurities on metal surfaces, very decisive places. And what you see here, for example, is copper nitride surface. The copper nitride is used instead of copper because then the coupling between the atoms and the surface is a little bit weaker. And you put cobalt atoms on the top, and then you have a magnetic impurity, the cobalt atom with a partially filled D shell, which is weakly coupled to the copper nitride below, which is an insulator, but the copper below the copper nitride is a metal. And then you have again a theory where some spin degrees of freedom are coupled to the bath. In fact, if you go into the literature and look for what is called magnetic molecules, right? Magnetic molecules, you will find a vast literature on people putting magnetic molecules on all types of surfaces and trying to find how their properties change as function of coupling to the surface, properties of surface, and so on. So it's all connected to these quantum impurity problems. Huh? Oh, this is actually an STM, scanning tunneling microscopy picture of the surface. And so basically what you see here is, I should be careful not to, the more or less, flat part is the copper nitride surface, and the spiky things are the cobalt atoms. So it's topographic, basically. Okay, so you see there's lots of interest in these quantum impurities, let alone the DMFT. I mean, this is another thing. This was the experimental part. From a theory, in fact, and that's what possibly Vijay and Antoine has also made clear already, they present a paradigm for correlation effects in solids. I mean, they are a simple system, but they contain all the correlations in an atomic multiplet. That are present in atomic multiplets, and those are the building blocks for the correlations in the solids. So these are the paradigmatic models for studying correlation effects in solids. They have a very neat feature. Everybody's talking about quantum phase transitions, and these models can actually show quantum phase transitions, but they are boundary quantum phase transitions. But nevertheless, you can study different kind of possible quantum phase transitions, like is there really a quantum phase transition if you have level crossing? What do you need for characterization of a quantum phase transition, and so on, by using these more simplified models, where you possibly have techniques to solve them easier than the Condor lattice or Hubbard model in 2 dimension at 0 temperature. They are, and this is what we just learned from Antoine's beautiful lecture, the ingredients for generalized mean field theories. I'm going a little bit beyond DMFT. The DMFT is basically the simplest version of that. He told you if you want to include short-range correlations, you might want to consider cluster mean field theories, and in that case, you have not only a single site or atom, but you have a collection of atoms on a certain connected lattice, which generate your quantum impurity in that case. That's okay. This is the quantum phase transition. There is one quantum phase transition in a certain model called the two-channel Condor model. If you like, there's a okay, never mind. Can talk about this. And there are, of course, potential devices for spintronics, because you can build these things using these nano-structuring technology, and hopefully you can realize single spins in a quantum dot and manipulate them very neatly, and also store them, get them out again. Coherence times are a different story then, and decoherence especially. So the general observation is that the models for quantum impurities are sometimes very simple. The Condor model is extremely simple from that perspective. Just one spin coupled to a non-interacting electron gas, we could say, well, this must be solvable. In fact, it is not. The physical properties of these objects are highly non-trivial. Even for the simplest Condor model, we will see later on that the physics are really very rich already on that level. And now imagine you put this into a DMFT, where you in addition get at least some ideas about lattice, and then this can become extremely rich. The actual problem, and that's why I don't want to do a blackboard talk here, because I can't present you any solution, is that if you want to solve any of these quantum impurity models, starting from the Condor model and going to the multi-orbital, multi-site, cluster DMFT, whatever input, you need state-of-the-art computational tools. There is no simple analytic formula of a solution that gives you the account to the physics, especially if you want to have real numbers. And that's actually what is the second part of this lecture series. After mine, you will learn this afternoon about perturbational approaches, and based on this a Monte Carlo technique that allows you to solve not the Condor model, but the related Anderson model. And on the next 3 lectures, you will be introduced to other techniques that allow you to solve these models with modern computational tools. Okay, so let us now try to get an idea what I mean by highly non-trivial. And the best possible effect one can discuss in that connection, and it's a very well understood and old example, is the Condor effect. And that's what I want to talk about in the next, 40 minutes roughly to you. What is it? Where does it come from? And in fact, what is the implication? Okay, I should work on my translation. So the Condor effect and the Condor problem. There was an experiment in 1934. You see, this is already 80 years ago, so it's a very, very old physics we are talking about, but nevertheless it's still absolutely present and relevant for the modern understanding of solid-state physics, especially correlation effects. This was the group of de Haas, de Boer, and van den Berg, published in Physica 1934. I think you can get this online here. It's in German as far as I remember. And what they do is they measured, this was shortly, well not shortly, but after the discovery of liquid helium, so you could cool down things to very low temperatures. Here you see the scale is a few Kelvin, and I think this was gold or some metal. And what they observed is that the resistance as function of temperature went through unexpected but wonderfully developed minimum. Now, in 1953, H. Wilson, that's not the Wilson from the Wilson energy, commented in The Theory of Metals the cause for this minimum is entirely obscure and constitutes a most striking departure from Mathieson's rule. And Mathieson's rule says the inverse lifetimes due to different scattering channels in a resistance simply add inverse lifetimes. So it's always like the parallel of resistivity, you add the inverse, and this is dominated by the smallest one. Some new physical principle seems to be involved. So the standard observations, phonons go like 1 over t cubed. The impurity resistivity is more or less a vegetable. So there was nothing around that could actually explain why there should be a minimum in the resistance of such a system. Okay, so then came the first observation: the occurrence and the position and the quality of the minimum depends on the sample. So it might be scattering from impurities, nevertheless. So let's try to do a theory for that. And I don't want to go through all the details, but what you can do is you can show that the resistance or resistivity of the impurity is given by this nice prefactor times 1 over the scattering time of the impurity, which is can be a function of T, temperature. Now, it's always complicated to do a scattering theory in the systems. You have these kind of randomly situated impurities, so you have to think about how to treat the randomness. But if you do that in a standard way, you will find that the impurity scattering rate is indeed some prefactor, which depends somehow on this concentration of the impurities, times a factor which goes like 1 plus alpha kBt over EF squared. That's a typical result you get in any of these calculations. And since we are at 3 Kelvin, 4 Kelvin, 5 Kelvin, maybe 10 Kelvin, and EF in any of these metals is 1 eV, 10,000 Kelvin, or even more than that, you will go with me that this is a factor which you can easily ignore. And secondly, it doesn't give you a minimum, no way. So it just goes up. So this can be roughly replaced by 1 over tau impurity 0. And then the left are the phonons, and as I told you, this goes like 1 over t cubed or something like that, and no minimum. So that doesn't work. Still, we know somehow has to depend on the quality of the sample. Well, then there was additional experimental evidence in the early 60s, late 50s, early 60s, and I show here some experiments by Kloxton and Zacharovic. Namely, if you take the series molybdenum, niobium, and deliberately put iron into this system. Iron now is again D shell transition metal iron, which has an open a D shell, and thus will exhibit a magnetic moment. And what you find is that depending on the system here, in fact, you can generate the minimum by going through a series, and there are ways from, I think it's from susceptibility measurements or residual susceptibility measurements to check whether there is a magnetic moment in the system or not on the iron. It turns out that as soon as you go through the series here and you see when the minimum appears, at the same time there appears a moment on the iron. So minimum and a moment on the iron are obviously somehow related. But that tells us that quite obviously the simple assumption of impurity scattering by some elastic potential will not be the proper way to describe it. And that's what, that drove Jun Kondo in 1964, that's a more recent picture of him, to write down this Hamiltonian I've shown you before. He said, okay, fine. There seems to be a magnetic moment around. Now, what do we know? The magnetic moment will be some spin. The spin will couple to the electrons by some J. And we know the SD model from the transition metal ions is some capable of describing at least physics in these systems. Why not assume that we have a similar model here and try to find out what are the properties if one now tries to do a scattering theory for that type of model. So that was the basic starting point. Okay, now we have to do a yes, sir. No. Here it's temperature. So here you see this is the resistivity again as function of temperature, as shown before, and you find this minimum. On that case, it's the No, these okay. This is the temperature axis, and these are different combinations of molybdenum niobium. So this, I think, is. I can't read it myself. Sorry. It's just increasing. This increasing niobium. Yeah. I'm sorry. The second plot. The second plot is basically this series here at a fixed temperature, higher temperature. So this is the composition. I'm sorry. This is the composition molybdenum niobium, starting from niobium and going over to molybdenium, right? So that's basically taking for each of these materials. What they did is they measured the impurity susceptibility by subtracting off lattice parts and so on, and from that extracted a guess for the local moment. Okay. Good. Yeah, so let's now become a little bit more specific and try to calculate the resistivity for that model. Now, I hope you have heard a little bit about solid-state physics during your education, and you have heard also about scattering theory, and at some point somebody told you in order to calculate resistivity in a solid, you have to calculate the scattering matrix from the impurities. I mean, this is in terms of a CPA type of approach, or in terms of CPA type of approach. That's the object you need to study resistivity in a solid. The T matrix basically is what you have to calculate is the ingoing scattering wave function, outgoing scattering wave function times the resolvent evaluated at some omega plus I delta times the scattering potential. Okay, so let's do that within a perturbation expansion. Now, what type of scattering events do we have? Well, this is I try to picturize that here. Those who know Feynman diagrams may be well off. The others just think of it in physical terms, namely, here we have our local spin, represented by this dashed line. Here we have a bent electron coming in, and here it's scattered out again. So there's a k associated with that line with some spin sigma. Here's a k prime associated with some spin sigma prime, maybe. And now let's look at the process where the conduction electron with spin up is scattered to a conduction electron with spin up. Different k, but doesn't matter. And that's, of course, controlled by the impurity SZ operator. So J times SZ, and this is the process you can have. So the next possibility is a bent electron with spin up comes in, and a bent electron with spin up goes down. But in the meantime, there's some scattering happening. And the scattering can now be different types of scatterings, but one possibility is that, in fact, you flip the spin up to the spin down on that part, then a spin down, one electron is propagating along here, and you flip back the spin down to the spin up, so the spin up is going out here. And that's, of course, represented by an operator J squared, S plus, S minus times S plus. So up to down and down to up again. And in between, you have to propagate an electron. Now, electrons are available 1 minus f from epsilon k. That's the unoccupied states. And you have the energy denominator z minus epsilon k. That tells you these are the energies where things can happen. But there's a second possibility. Namely, you can actually move the electron here, then have a hole propagating back, not an electron, but have a hole propagating backwards in time, and then spill out the electron again. This is a so-called exchange process. And you know quantum mechanics lives on these exchange processes. Otherwise, Hartree theory would be very boring. It's the Fock term. That's the exchange term in the simplest possible theory that gives you all interesting physical effects like changing of the band structure, also gives you a nasty effect like this cusp there, but exchange hole and so on. It's not the Hartree, the classical term, it's the exchange term. And again, here you have the exchange term, which we will see in a moment is the one that gives the physics. Okay, now here the point is one has to use the opposite opposite way of the operators. So here have S minus, S plus, here have S plus, S minus, and since S is a quantum object, those operators do not commute. So S plus, S minus is equal to H bar SC, which is not 0. So what you see is you can actually now commute, for example, that object here by replacing S plus, S minus by S minus, S plus, plus SZ times whatever. And then what happens is that this guy, after commuting, cancels this Fermi function here. So there's left S minus S plus times 1 over Z minus epsilon k, but you retain an SZ times Fermi function, which then goes together with that one here. And if you go through the details of the whole derivation, what you find is that this scattering matrix can be written as J times SZ, that comes from that part and that part, 1, this is this one, plus J over N times the sum over all states K, Fermi function, a lone Fermi function, divided by Z minus epsilon K. And then there's a second term which contains simply a sum over the bare propagator, and if you evaluate that, that's simply 1 over EF, so you can ignore that one. This is the important one. This one gives a small contribution. Okay, next step. You can actually go through all these other matrix elements. There are lots of them, so I don't want to go into details. But eventually what you find out, if you do the calculation and then collect all contributions into the expression for the inverse scattering time, which is proportional to sum over all scattering channels squared, evaluate the integrals. This is some k-sums involved and so on. There's a sum over energy involved, which I don't want to talk about here. But what you do, and I think you may actually, oops. Okay, sorry. Once again, this is the disadvantage when you use those. The thing is the Fermi function. What is the Fermi function? The Fermi function does that one at the Fermi energy. And then you have an integral over k. Now assume you do this integral, assuming some constant density of states, you have an integral from minus bandwidth to 0 over 1 over Z minus epsilon. And this gives you a logarithm. And the logarithm is a very beastly thing. It diverges in both directions. So minus D is fine, but the 0 gives you a logarithmic divergence when you're at the Fermi energy. Aha. Logarithm, fine. And if you now collect all the contributions and actually do the integrations properly, you find that tau of epsilon does contain this logarithmic part, log epsilon over epsilon f. And if you then put this into the, for example, Boltzmann equation or kind of scattering time approximation for the resistivity, then you end up with a resistivity which is proportional. I ignore all the prefactors, they are unimportant, which is proportional to 1 minus 4 times J times density of states at the Fermi energy times log of kBt over EF. And now you see two things. First of all, if J is negative, and remember my Kondo model was defined band states plus J times spin-spin interaction. If J is negative, we have a ferromagnetic coupling. That is the old SD model. We have a ferromagnetic coupling, then this term, this is the wrong sign, I'm afraid. Come on. Yes, this is the wrong sign, it has to be plus. So if J is negative, then the combination, and T is small enough, then log is negative, so we have altogether a positive, no, it's right, sorry. If J is negative, we have a positive sign here, the log gives us a negative sign, so if 1 minus something, and this as function of temperature goes down. So nothing happens. However, if J is positive, then we have a minus J times log of a kBt divide BF. Log is negative, compensates that one, and then, whoops, R of T goes up logarithmically. So this actually gives you an increase in resistivity as function of temperature for low temperatures. This is the new physical effect Wilson was asking for, because now you can have, if you add those different scattering channels, actually formation of a minimum. And that's what Kondo then did. He took basically, okay, that's what I just said. There's no problem here. But if you have antiferromagnetic J bigger than 0, you have a logarithmic increase of the resistivity for low enough T, and this is the Kondo effect. And now what you can do is you can fit this to experimental data. This is experimental data from different systems. And what Kondo did is he took a resistivity proportional to T cubed for the phonons, he took some residual scatterings due to impurities plus the Kondo contribution log KBT over EF, and then could get these wonderful fits for the functions here. So that explains the effect. It gives a physical meaning because you have the scattering, and the scattering from those spins, they obviously produce an increase of the scattering rate at low temperatures. Okay, so one could say, fine, that explains the experiment, and let's go for coffee now, or for lunch. Well, I'm not quite. Okay, since I still have half an hour, we don't do that, and think a little bit more about what we have just done. Namely, there's a small problem. You might have realized the logarithm doesn't stop to increase as you go to t equals 0. In fact, it diverges. And of course, nobody ever observed diverging resistivities, impurity resistivities in these materials. In fact, what you observe is that the resistivity does that. It wonderfully saturates as t becomes very small. And you can do even more. You can actually follow the behavior of this resistivity curve here, and what you observe is that it is proportional to t squared. So there's no logarithm here anymore. You may find logarithms down here, but there's no logarithm anymore down here. So that's a small problem, and that's can be tried to resolve that by standard approaches. Yes? Oh, wait. The minimum is over here somewhere. Yeah, so look at the scale here. So it's pretty high, and the temperature is very low. So you have to go out to
this one, the previous one.
Oh, I see. Yes, sorry. There is no minimum there. Good. I'm sorry. I thought I'd do a good thing here using this funny. That's again. Why doesn't it work now? Okay. No, nothing works anymore. Here we are. Okay. Not too quick in pressing the button. Now. Okay. So actually, if there you see the minimum. So here, what Kondo did actually is adjust to these lower temperature data. So you have the logarithmic increase. So the minimum is basically at somewhat higher temperatures.
Here the minima.
It does. Well, here you have a minimum. It goes up. It goes up again.
Okay.
After some temperature, it goes up again. I mean, the point is that you have additional phononic contributions, so the contribution by the logarithmic part must be larger than the phononic part. Yeah? And as soon as that happens, you start to increase. Okay. So, right. Now, let's try to solve the issue, and the way theoreticians, when they see that perturbation theory gives some interesting result, they try to continue with the perturbation theories. And what you can then do is try to do self-consistent resummation of things, Parquet equations. There are wonderful names for all these things. I don't want to go into detail here. You can take a look at Alex Hewson's books. Explains that quite nicely. What it boils down to is that you actually can resum the perturbation series. It's called locked leading divergences. And you end up with an expression for resistivity or resistance that has that form. Now again, if you now put again J less than 0, meaning you have ferromagnetic coupling, what you see is that this one is negative now. This one is for small temperatures also negative. Now this diverges, but that doesn't really make a difference because R would go to 0 then. So for ferromagnetic coupling, everything is wonderful. That's we had also a problem there because then it would go to minus infinity. This has been resolved. It goes to 0. Good. Nothing apart from simple impurity scattering for the ferromagnetic model. On the other hand, if you now introduce an antiferromagnetic coupling, okay, there's something missing. If you introduce an antiferromagnetic coupling, that means J is positive, then this becomes negative, and at some point you have replaced a small problem by a big problem, because now this whole thing diverges at a finite temperature. And this temperature is given by the so-called Kondo temperature, Tk, which you can basically read off here as e to the minus 1 over blah times j. And that tells you this is a non-analytic behavior, so there's no way that perturbation theory might do anything good. And this is the Kondo problem. So you have now a finite divergence of the finite temperature, and the whole theory, as nicely as it might explain the minimum and the region around the minimum, does tell you there's something more in it, and we don't even close to capture these physical aspects. Okay, and I think this was around 60-something, and then it took about 10 years until one really understood the physics of this system, roughly 10 years, physics of the system completely, and the method that more or less solved the whole issue and made the physics as clear as possible was introduction by Ken Wilson with his numerical minimization group. We will talk about this later. Okay, so this is a Kondo problem. And then there are several other experimental facts, in fact. And now one can, this started to become an industry in the 60s and 70s to collect facts to understand the physical properties of these systems, at least from an experimental point of view. And then the theory tried to, well, walk behind and develop methods and tools which allow you to do calculations to solve these issues that have been posed by experimentalists. Names along that line are Müller-Hartmann, Sittards, Anderson, Haldane, Lama Yafet, and so on, Takahashi. Lots of people have been working on these things. Okay, so what we know right now is at least that's the experiments. That's what the experiments tell us. If we have a T much larger than the Kondo temperature, that's now a scale that somehow signals there is something going on in the system. Yeah? In theory, it tells you, stop, you can't do anything more here. From the experimental fact, it seems to be that at that point there seems to be crossover between different regimes. So if we had temperatures much larger than T, we observe a free local moment. That is, if you measure the local susceptibility of those impurities, they appear to go like 1 over T with a prefactor which is a free moment and usually fits quite well the moments of these impurities added there. If T is much smaller than Tk, what you observe, in fact, is that the chi is a constant. Now, chi if constant means you don't have any local moment, it's a vegetable. Also, what you observe is that the specific heat you find is also a constant. C over T is a constant. And as I told you before, if you measure the resistance at low temperatures, it deviates from the zero temperature resistivity like a T-square law. But these are things we know. I mean, this is something our guru for phase transitions has also told us how to treat interactive fermion systems. This is like a standard Fermi liquid. This looks like a Fermi liquid. Yeah? So in Fermi liquids, you have a constant Pauli susceptibility. You have a constant Sommerfeld coefficient. And the resistivity, if you do the calculation correctly, varies like T squared. So what has happened? Yeah? The consequence is that, and this was, I think, Nozier in 1972 or something, about that suggested, is that one actually has to call the ground state of this Kondo model, or has to interpret the ground state of this Kondo model from these experimental facts. Yeah? At that time, one didn't know the theory for that, but from the experimental facts alone, that the ground state of a Kondo model is a singlet because there's no moment anymore in the system. Yeah? Here you have a moment, but here you don't have a moment. So the only thing that's left is a singlet. And it's low energy excitations. And these are contained in specific heat, resistivity, and behavior, temperature behavior of the chi. And its low energy excitations are those of, in that case, because it's restricted to the impurity alone, a local Fermi liquid. And you might now already see where the journey is going to. We always talk about Fermi liquids in our DMFT calculations. Where do they come from? Well, here they are. We just have to find them somehow in our calculations. So that's what experimenters tells us. A local Fermi liquid is a system where if you look only at the properties of the impurity, Yeah, you don't care for the electrons around. You just look at the properties of impurity. Then the excitations of this impurity system have a structure of a Fermi liquid. Meaning you can relate them to a some, I don't know which, but some non-interacting electron gas that has the same structure of levels. That's all that tells you. But this is already sufficient. I shouldn't be that fast with clicking here. That's what slows down a presentation. The important point is that these are local quantities. So I don't talk about the lattice here. Yeah? I just talk about what the impurity contributes to the lattice. And that's a local contribution. And this tells you that this type of behavior is similar to a Fermi liquid. Now, a Fermi liquid is, of course, something which is usually in a lattice, but there's no reason why not assuming you have an impurity system that has a certain set of excitation energies, and those excitation energies behave like a Fermi liquid would predict that. So there's nothing, it's just a name. Further questions? Yeah?
So we have this.
Take the mic, please.
Oh, so we have this impurity which has sort of a two-level system, so we can associate some entropy to it.
Yeah.
So what happens to that entropy at when it becomes a singlet? When it's quenched?
It goes to zero. The entropy is quenched.
So how does one understand it's decreasing then? Entropy is decreasing as one goes to this low temperature scale.
Yeah. Actually, that's precisely what happens. If you have the spin itself is an is ln2, basically gives you an ln2, and of course, if you would go to t equals 0, this would violate third law of thermodynamics. Yeah? So what the system does is through the interaction, there's an interaction between the band states, which itself has a vanishing entropy, and the impurity. They screen this local moment. They remove this degeneracy from the system, and they do that by forming, and we will see that later, they do that by forming a singlet between the local moment and a band electron around that. So that's no new object, that has zero entropy, and of course, since you have an infinite system of band electrons, they don't care if they miss one or not. Yeah? They are happily still a Fermi liquid. Okay? Okay. So far, what we have found is that the non-interacting ground state has a local moment. That's what you were just referring to. We found that the interacting ground state is a singlet. Now, quite obviously, those two guys, they don't go together. Yeah? So the overlap between a singlet and a local moment has to be zero. And that's also called Anderson's orthogonality catastrophe, which means that for this model, or those types of model, in fact, if you take the overlap between the non-interacting ground state and the interacting ground state, if you go into the thermodynamic limit, that's quite important. Yeah? In fact, this will go to zero like an algebraic function. This overlap goes to zero. So, and that tells us another thing, namely, if we try to do perturbation theory, we usually start from that object here. And since those are orthogonal, there's no way in perturbation theory to go from here to there. There's no way. Yeah? You just walk in that space, and whatever you do, you don't come into that direction. And that's what we saw in the previous calculation, namely this manifests itself in these logarithmic divergences and the unphysical behavior, for example, of properties. Now let's try to okay, several questions. First of all, where does this local moment come from? Oh, okay. Where does the local moment actually come from? Yeah, I said, I don't care where it comes from, it's there, I have an exchange reaction. Second, where does this interaction arise from? Hund's coupling always gives you ferromagnetic, so that can't be the reason, there must be something else. And then the question is, why is a singlet formed? And how can one generate a local Fermi liquid? Well, this is funny. Question, why does that happen at all? So we need a little more realistic model to really answer those type of questions. This one could try to do from the Kondo model, but let's try to be a bit more realistic. And that brings us to the Anderson model, single impurity Anderson model, Antoine already introduced in his lecture. So the experiment tells us the electrons are sitting in localized open shell orbitals, like in cobalt or iron or cerium or whatever, and those lead eventually to the Kondo effect. I mean, this is the experiment. So let's try to set up a model for electronic properties of such a system. And again, let us start with a picture. So again, we have here the energy axis. Here we have the density of states now. And we assume we have a band electron system, which is this box here, typically filled until the Fermi energy. And then let's put localized orbitals on the atom. So one sitting at an energy epsilon d, somewhere below the Fermi energy, should be filled, so otherwise we wouldn't have local moments. And the second one sitting at some energy epsilon d plus u above the Fermi energy, because if that also would sit below the Fermi energy, we wouldn't have a local moment, we would have a singlet again. That's what Antoine already alluded to. And of course, they have to talk to each other, otherwise the system would be rather boring. And we do that by allowing them to exchange electrons. That is, this electron might actually hop from there into the localized orbital, or out of the localized orbital, or into the doubly occupied state, or out of the doubly occupied state. Okay, that's the picture, and that's the formula, and that's called Anderson Hamiltonian, and you've seen that before on the blackboard. We have here the band electrons, again some dispersion. I don't care, that doesn't really matter, most cases, times the number operator. Here we have our impurity, epsilon d is the position of the level. If you put a second electron with opposite spin, otherwise Pauli would say, you have to pay an energy U. And of course, you need the hybridization, that is, a band electron can transform into a d electron and vice versa. That's the Anderson Hamiltonian. It looks as simple as the Kondo model, a little bit more complex because you now have charge degrees of freedom, but otherwise it's not very complicated either. Okay, so what can you do with that? Well, the first thing is you do Hartree-Fock. Fock doesn't exist here. In my case, Hartree means you take the n sigma, n minus sigma, that's the two-particle interaction term, and replace one of these guys by its expectation value. Antoine told you that's the worst thing you can do, but let's do it nonetheless. And what you then have to do is you have to go through some algebra, which is you can find in Alex Hewson's book, or read the original article by Phil Anderson. I can just recommend to do that. It's a wonderful article, actually. And what you find is that there are two regions in the system. One might call paramagnetic region, and that is the case when a certain parameter, namely pi gamma naught over u, where gamma naught is the hybridization function Antoine already introduced. Now, since I have a constant density of states, my gamma of omega is a gamma naught, basically, which is given by pi times density of states of the band electrons at the Fermi energy times d squared, Fermi's golden rule, charge fluctuation rate. If that is this quantity is larger than 1, that means u is less than this magic number, we are in a paramagnetic state. Boring. If that this object, especially at half filling, so this is the filling 2, 1, 0, at half filling, if that crosses the line pi gamma naught over u equals to 1, then something happens. And in this mean field treatment, since mean field never cares, or especially this mean field never cares about any dimension, it also orders in one dimension, and what you get here is a ferromagnetic ordering. Well, this is of course nonsense, right? So in a zero-dimensional system, impurity here, you wouldn't expect any ordering. But of course, it tells you that once you cross that border here, the physics of the system has to change, because then the system wants to develop a local moment. Now, of course, fluctuations, quantum fluctuations, will not allow to do that. Otherwise, you would have really a phase transition, and that can't be. So that must be kind of crossover. And of course, the existence of the local moment, again, would signal as phase transition. So somehow the system has to avoid really going into an ordered phase where you have a static local moment. So that already tells you that there must be something going on that makes this local moment dynamic in some sense. We'll see later what that happens. So there's appearance and, of course, an unphysical phase transition. This is all quite nice. So now we may understand where the local moment comes from. Meaning, okay, we have our cobalt impurity or iron impurity in the metal. The parameters are such that this atom is in this region, and we do have a local moment. Now, where does the Kondo model come from? Where does the antimagnetic exchange come from? Where does the Kondo effect come from? And that's actually what Antoine also talked about. So he gave most of the things I tell you right now. He has already given in his lecture. The Kondo model should work deep in the local moment regime. So we want to have a rather stable local moment, and the rest of the interactions should simply must be there for removing the entropy. So we go into the regime of large U, where we know that from Anderson's analysis we should be very much on the side where we have a stable local moment. And this has been worked out by Schriefer and Wolf in '66. So we don't have any real charge fluctuations, but we have virtual one, as Antoine told us. And now we consider a second order perturbation process. And this is the two possible situations. Now, this here is the band, a sea of conduction electrons. This is the local level sitting at epsilon d. This is the doubly occupied level sitting at epsilon d plus u. We have a band electron, say, with a spin down coming. We have a localized electron sitting here with a spin up. So what can happen? Well, in fact, this guy can go up and this can go down. So what does happen here? You just exchange those two guys, which is a process V, so V squared, and the energy difference is epsilon d. So this is a process that gives you a contribution V squared over epsilon d. There's a second one, again, exchange is where the physics come into play. And this is the one where now this electron can move up here. Well, can move into the localized level when the second electron is still here. Well, this means you have actually to go up to the second level, and that's this process. Now, maybe this was a little bit fast. Let's, nine. I hate my. So there's also a way to slow things down. Okay, now take a look. You see that this goes up, and then actually this guy comes down, and this goes into the band. But this means, remember, the down electron was sitting there, the up electron was sitting there in the intermediate state. So you have to remove that electron from the impurity, going around once and then going down. But going around means you acquire minus sign. Yeah? Okay. Acquire minus sign here. Again, it's V squared. Now the intermediate energy was epsilon d plus u, but you acquire minus sign here. That's very important. And then you add those two things together, and I hope you can read this. And this is called Schriefer-Wolf transformation, namely the Anderson impurity model, say especially the term epsilon d plus u half plus hybridization, in the limit that epsilon d and epsilon d plus u are much larger than this fluctuation scale gamma 0. That's the fluctuation scale. If these are much larger than that, you can actually map this Hamiltonian to a Kondo exchange Hamiltonian, and the prefactor is V squared over U times divided by epsilon D times epsilon D plus U. And that's a positive quantity. So this is a exchange interaction with a antiferromagnetic exchange. So precisely what you need to get the Kondo effect. Actually, that's very similar to what Antoine showed. If you only take the details, here you have V squared, and here you have 1 over epsilon D. Epsilon D is something like the interaction energy. So V is the hopping, V squared over epsilon D was the V squared over U we had in the Hubbard model. So that's the reason why, or that's the actual proof that the Anderson model in the proper limit, namely large U, localized moment, really has the physics of the Kondo model with an antiferromagnetic exchange. So you really have Kondo physics. Both models show the same physics. Again, in the limit that the level of the localized level and its doubly occupied counterpart are way above and below the Fermi energy. Way above means much larger than this fluctuation scale gamma naught. Your low energy features of the Anderson Hamiltonian will be equivalent to those of the Kondo Hamiltonian with antiferromagnetic exchange coupling. Okay. So what's special about AF coupling? And here we can, again, use something that Phil Anderson proposed and Duncan Haldane, namely something called Poorman scaling. And so those who are not really familiar with these renormalization group arguments, beta function and kind of things, They just try to get the main idea. The others will probably recognize things anyway. So what you do is, remember these were the band states. This was the box, the band states here, the Fermi energy. And what you now do is you say, okay, let's try to focus on what's going on here. So let's say take a magnifying glass. What a magnifying glass does, it basically projects out everything at high energies and tries to focus on the low energies. And projecting out at high energies in the language of many body physics means you integrate out the high energy degrees of freedom by some way. Since you have been introduced to path integral formulation, you can actually think of how this has been done. Has to be done. You take the states or the Grossman variables which live at high energy, perform that integration, and then what you then get is renormalized action. And if you then try to rewrite this renormalized action in the form of the previous action, you get a connection between what you basically between the old interaction and the new renormalized interaction. And what you then get is some kind of differential equation or better function for the running coupling constant. That's also what people in high energy physics do all the time. And for the quantum model, it reads dj over d log d is 2 times n of EF times j squared. So that's the differential equation. And now you can try to understand what the solution of this equation is. And there are two actually equations. Namely, if you start out with a initially ferromagnetic interaction, that is G, where the band cutoff is still at D, is less than 0, then you can see the flow because the J starts at a negative value. The right-hand side is positive, so it increases and becomes smaller and smaller and smaller and smaller. And at some point, the fixed point will be J of D equals 0 is 0. So if you integrate this equation from starting, and the right-hand side is positive, so everything goes up and up and up. And that means you end up, when you integrate the flow simply without thinking, you end up actually that J at D equals 0 is infinity. And that tells you there's no way that recoupling can be any good. Even this equation, that differential equation that gives you the flow of the coupling constant has to break down at some point. And what you have to do is you have to look into the strong coupling behavior. Now, but it tells you also something. Because this J goes to infinity, the physics of these models will be such that the coupling is growing and growing and growing. So the more you look at low energy states, the coupling between those low energy states and spins becomes stronger and stronger and stronger. So there will be a singlet formation. That means the system of band electrons and the local impurity will form a singlet because of that effect here. And there's one invariant of the scaling flow, and lo and behold, that's our well-beloved Kondo temperature. And that tells you you can actually rescale everything in that equation by just dividing out this energy scale, and that means the flow is universal. It doesn't depend on, it does just depend on J over Tk, but not on the actual parameters. So you also would expect that at low enough temperatures, of course, your models will exhibit some universal behavior, namely all the observables should be depend only on T over Tk, not on T individually anymore. That's also one effect in these quantum purity systems. You typically find a region where you have universal behavior, that is, there exists a low energy scale, and everything depends on energies over this low energy scale only. Okay, now this was the story, basically. Ooh. As I said, 2.5 hours, I think it's okay. So standard analysis model, one spin generated level. The realistic models, orbital and spin degrees of freedom. Antoine told you, there are 5 or 7 in D or F electrons. So there's not one. So it's easy to generalize. I mean, he has also written down this. You can have, again, here a more or less complicated Hamiltonian for the band electrons. You have this localized level. You have a very complicated Coulomb matrix. You can calculate this object from Slater numbers and these kind of things. Fine, no problem here. And you have the hybridization, which I don't write down. It's just, again, the same structure as before, but now the hybridization can be also, must be not necessarily diagonal in the orbital indices. There are consequences to physics, and this has been worked out by Koblen and Schriefer, Nozière and Blondin and others. I mean, this is the oldest thing I know about that. Maybe there's even older stuff. Actually, there is not very much that changes. There's mainly a renormalization of scales. That's one aspect. So you also can still find kind of Kondo physics. There may be different scales involved. The scales may not depend exponentially anymore, but otherwise there are very similar physics, in fact. But there are also novel features, and these novel features can become very important if you plug this into a dynamic mean field calculation, for example. Namely, you can have, because now you have more than one orbital quantum number, you can form larger spins, for example. Yeah? And if you couple, for example, spin 3½ to a spin 1½ electron band system, you might wonder how does screening take place there? How does this spin will be compensated? And the answer, it can't be. I mean, there's not enough states available, but what you find is under-screened Kondo effect. So a part of the spin will be screened, and this gives also rise to quite interesting behavior of the physical quantities. Since orbitals are involved, you might also have orbital Kondo effect, or both, or whatever. And because now this Coulomb matrix might actually do the job for you, you can form local singlets by itself. Then there's no Kondo at all. That's a vegetable by its own. So, and of course, you might wonder how you generate all these different states. Now, this is due to the parameters that enter here. So material dependent, model dependent. Yeah? And of course, if you do kind of DMFT, the self-consistency can actually very subtly modify the coupling here. And this modified coupling can actually generate all these effects. And this already tells you that the physics of the DMFT, although it at the first point seems a little bit harsh to replace a lattice by some impurity object, can become very, very rich due to this rich physics of these impurity systems. Okay, so that's the first part of my lecture, and I would like to make a brief stop here, take a breath, and if you have questions regarding Kondo effect, Kondo problems, so on, you should ask them now, or wake up. I hope I wasn't too fast. I mean, I should have said in the beginning, stop me, break me. I want to convey a message and not give a scientific talk for the experts auditorium. So in any case, you should stop me and ask questions and slow me down if I'm too fast. This is now too late, but yeah, that's a question.
So I mean, the experimental curve that you showed actually, like as you go down the temperature, it decreases and then show the upturn, right? But what Kondo explained is, I guess, the logarithmic behavior below the Kondo, and that through the perturbation theory.
Yes.
Okay.
So that, but it's only that effect you can explain that region where, so to speak, correlations start to enter the game. That you can describe well by perturbation theory. But as soon as you go to lower temperatures, then perturbation theory, due to this flow to strong coupling in this renormalization sense, breaks down. And then you have to do something else. And that's what I want to talk about now.
And okay, so you showed actually some diagrams actually. So is there like, I mean, when you do the perturbation actually, so is there the only those diagrams are important, or doing?
No. Actually, this is the second order contribution. There are these are the only 3 diagrams up to second order, but you have different matrix elements. So you have spin up, spin down, spin down, spin down, and so altogether I think 16 or so of that sort. But if you go to third order, then that becomes a mess. So you can think about how to construct these different diagrams. Now what you will find actually diagrams which are, in the sense of perturbation theory, reducible, so they fall apart into the product, but there are also diagrams where everything crosses, and these are a mess. Yeah.
If I start from the Anderson model, by Schrieffer-Wolff transformation, I will get a ferromagnetic coupling and an antiferromagnetic coupling, both terms.
No.
Oh, the first the Hartree diagram, will that give a
Sorry, Schriever-Wulff doesn't have a heart tree.
oh, sorry. Yeah. Oh. Okay. So this Anderson model will reduce only to a antiferromagnetic thing, is it?
There will be a second term, but this is a potential scattering term. So we get a potential scattering term, which is, but this is only relevant if you're not at a particle-Hole symmetric limit. So if you're away from particle-Hole symmetry, but there's only this second order antiferromagnetic term.
Okay.
Right. There's no Hartree term in that kind.
The simple exchange thing that you had shown was coming with a different sign of v square by ed.
Yep.
Is that the ferromagnetic thing? Or means
No,
there were
no.
two kinds of exchanges that you showed between the spins in the bath and the local impurity.
No, they both are antiferromagnetic, in fact. I'm sorry, the sign is maybe a little bit misleading, because you have to now, when you take those contributions, you have to rearrange your operators in a sense to get the spin S plus, S minus, and so on operators generated, and that actually gives another sign. So the minus 1 v squared over ed plus u turns into plus, and the v squared over ed turns into minus.
Okay.
So they both lead to antiferromagnetic couplings, and they add up.
Okay.
Otherwise, if the one would be ferromagnetic, the other one would be antiferromagnetic, you can create a crossover between ferromagnetic and antiferromagnetic. But those are both antiferromagnetic, and they add up.
Will it be right to, physics-wise, to understand these anomalies in the thermodynamic quantities we're getting, say, in resistivity, logarithmic divergences there?
Yeah.
So will it be to understand that there is a scale in the system which wasn't to begin with in our original Hamiltonian Anderson model, which we write for that.
Yeah.
So it will be, the physical explanation will be that there is a low energy scale which we didn't have in the original Hamiltonian, and that's why we are getting these.
Yeah, you can think of that, as I told you, if you increase U, the Anderson solution, the field solution would tell you have to create a local moment. Right. This is not possible. So at some point, this moment has to fluctuate. So you will have to have another new time scale introduced by the coupling to the surrounding, which makes this moment fluctuate between up and down, so that in the infinite time limit, the average is basically no moment again. Yeah. So for a long time, you see a moment, and then at some time, it starts to deviate. And this time, you can identify with an energy scale. And of course, the larger U is, the longer it takes for this moment to fluctuate, and the smaller this energy scale becomes. And that's precisely the meaning of the Kondo scale. So it's basically this flipping.
Yeah, and also in the original Anderson model, we have this hybridization, which is sort of charge fluctuation. We don't have antiferromatic coupling between impurity and these conduction electrons.
Yeah. Yeah, but this is a quite general aspect of these hybridization plus interaction. As Antoine told you, in the Hubbard model, it leads to antiferromagnetic nearest neighbor exchange between spins, and here it leads to an antiferromagnetic coupling between the spins of the band. And so that's a quite standard.
Yeah, that is when we get effective Hamiltonian Schrieffer-Wulff using Schrieffer-Wulff, then we get that thing.
Now the reason is simply it tries to remove the degeneracy, and the only way to remove the degeneracy is to form a singlet, because triplet is not an option. Okay, so everybody is taking a breath and is awake again. Now let's come to the second hour, namely how to solve these quantum impurities. And I just told you, they have a lot of interest in physics, but they're beastly complicated beasts when it comes down to solving them. The question is, how can one solve these quantum impurities models? And I would again draw attention to the literature here. For the more general aspects, you can look at the Kondo effect to fermions by Alex Hewson. And I want to talk about the numerical organization group, because you can also see then some nice pictures how that works. And here you find a recent review article by Ralf Buller and others. I would like to start now from a more general aspect, namely what is available. So there's a general distinction between approximate methods and what you would call numerically exact methods. I mean, there's also, if you like, there's also an exact algebraic method, beta ansatz, but this doesn't work for our purpose because it doesn't allow to calculate dynamics. This is mainly because absolutely mandatory, as you've learned from Antoine, you need the Green's function. You have to calculate self-energy. That is, you have to must be able to calculate dynamical properties with some reliability, at least for Matsubara frequencies. And what you also would like to have, but that's a really complicated issue, and I think there's only, to my knowledge, two approaches that allow to do that, namely these perturbation theories, access to ground potential directly, and then you can calculate entropy and so on for the lattice system. Now you can access specific heat through calculating of energy, but then you have to go back and calculate the entropy by integrating C over T, and this does only work if you don't have any phase transition in the Luring. If you have phase transition in between, then you have a problem. So it would be desirable, especially if you want to calculate different phases and see how the phases match to access the ground potential directly. That's non-trivial problem. So there are approximate techniques. And here I want to make a note. I also consider a discretization of the band electron system as an approximation. You remember this was a box, and the box is a continuum. And as Antoine told you, you have a delta of tau minus tau prime, which is a continuous function of tau usually, or gamma of omega is a continuous function of omega. And if you introduce a discretization of your band electrons, you will replace that by a series of delta spikes. And I consider this as an approximation because you have to think of how going back to thermodynamic limit. Again, all this I was telling you, Kondo effect, orthogonality catastrophe, and so on. This all happens in the thermodynamic limit. So you better take care of being at least approximately in this limit. Then there's a distinction between perturbative and non-perturbative approaches. The perturbative ones are perturbation theory in U. This will be a lecture by Michel this afternoon. There's a perturbation theory in V. This will a lecture by some guy on Wednesday morning. Or is it Wednesday or Thursday? I don't know. It's Thursday, sorry. Okay, so replace it by Thursday. There are non-perturbative methods, again, approximate. This is exactization because you have to replace your band electron system by a discrete set, a rather small discrete set of electronic states. Monte Carlo does not need to do it. Monte Carlo basically works in the thermodynamic limit directly. There you only have well, statistical and to some extent systematic errors. And of course the numerical renormalization group approach, which, as I will show you in a moment, is also based on the discretization of the band electron states. Then there are numerically exact techniques, the beta ansatz, which unfortunately doesn't allow to do dynamics, but if you are interested in the quantum impurity aspects only, you may want to look at the original paper by Zwellig and Wiegmann, or Pedro Schlottmann and, I forgot his first name, Sacramento, in Advanced in Physics in the early 90s. And then, of course, the huge, vast system Quantum Monte Carlo approaches, like the Hirsch-Phi algorithm, that was the old one. You can look at the article by Hirsch and Phi in 1888. It's a bit outdated because it has problems, certain problems. You need to discretize your time axis in that case, and take care that the discretization error doesn't spoil your calculations. Antoine knows that this can happen pretty badly. Then you have the continuous time Monte Carlo, which is the state-of-the-art method to access these quantum impurity problems. Actually quite variety and complex models you can study with this technique, and you will learn about this by Michel again and Philipp Werner on Friday. Okay, so let's go to the numericalization group, and now I have to hurry up a little bit. There are several papers you can read. The original RMP by Ken Wilson is very nice. You learn a lot of mathematics, also function theory there. I can just recommend it. Then by HRK, the paper that really did the application of this technique to the endless impurity model. There are two papers in 1980. And in fact, I can only recommend, if you want to use that method, take that paper, take the equations, code them, and run it. That works. I did it that way. So this is a wonderful paper, and anything you want to know about energy is already written in there. Again, Alex Hewson tells you a little bit about this too, and also how to calculate dynamics. And then if you want to learn more about calculating dynamics, you can look at our recent review. So as a reminder, the Kondo and Anderson model are plagued by infrared divergencies. Namely, properties, if you go to low enough temperatures in the Kondo regime, scale like log, in perturbation theory, scale like log epsilon or kBt, whatever you're looking at, divided by some cutoff. This has as a consequence that actually all energy scales from the high energy cutoff down to the desired energy scale somehow contribute. You can see that by writing log something over d is equal to log d over lambda over d plus log over of something over d over lambda when you pick the lambda, say, larger than 1 properly. And you can repeat this down to some desired cutoff here. That is, any renormalization collects everything from high energy, low energy. Now, this is a basic problem we have faced in the perturbation series, and Ken Wilson said, well, let's turn the problem into a feature and simply try to make this into a working algorithm. And that's how it works. And here now comes the pictures, and that's most easily be done really with the computers these days. So the implementation is, and these shaded pink area here is now the band electron density of states. And I just didn't take this box, but I took something rather complex here, which you might encounter in a DMFT calculation, for example. The only thing I require is that there's a finite support of this object, and which I call plus minus d. Actually, it can be 0 here and then somehow, but there must be a finite support. Otherwise, the whole thing doesn't work. Okay, so next step is we take what we just learned before and divide our energy axis into a series of logarithmically discretized things. Namely, here we pick up a lambda larger than 1. We divide this. First is lambda 1 over lambda. The second one has the width 1 over lambda squared. The third lambda third and fourth, and so on down to 0. And you do the same thing on the negative energy side in order to have this shell structure on both sides. And then within each shell, what you can do is you can write down a Fourier analysis of your band electron operators in this shell. So you take the energy shell, just take plane waves located in this energy shell, and then represent your operator here for this given energy shell as a Fourier sum over all these operators. Now this can be visualized in the following sense. You have here your impurity that couples to a set of states, these balloons. There's one certain state of the shell M, which has Fourier component 0. And then you, of course, have all these balloons of the same shell M with Fourier components L larger than 0. Yeah, so these generate those balloons. Now, so this was the first approximation within the energy. The other one that happens now is this. You simply cut off the other balloons. And the important thing is that you may have noted that only those guys here actually talk to the impurity. So these homogeneous components talk to the impurity. The other components come into play only indirectly by talking to these things. And you can actually show, that's what Wilson has done, Krish has done in his PhD thesis, you can actually show that the coupling between those guys and the other blue balloons goes like 1 minus lambda. Now lambda is close to 1, and we consider 6 close to 1, then this is always small. Yeah. That's the typical approximation you have to make. You pick a lambda that's not equal to 1, but you say, okay, the coupling is small in some sense. So that's the major approximation. After that, everything is now more or less straightforward. So what you have here is, if you like, an impurity in a star configuration talking to a still infinite number of states, but now only a discrete set. And the next thing is you do some kind of Lanczos tridiagonalization and transform that thing into a semi-infinite chain where the impurity sits at the beginning, and then there's a hopping between the impurity first side, second side, third side, fourth side. The point is that all these hoppings are nearest neighbor only, so you don't have a hopping from here to there directly. They just talk to the neighboring side. And what's also interesting, the hopping between the side n and n plus 1 decays like lambda to the minus n half. So this becomes smaller and smaller the further you get out with your energy shell. Well, and that can be used now to generate the so-called iterative degradation scheme and truncation. You start with the impurity region at one side, call that my H naught, diagonalize it, take the operators from that side, add them to the Hamiltonian, diagonalize that, call it H1, add the second side, diagonalize it, call it H3. So what you had is Hn plus 1 is some mapping from Hn. You can write down the mapping, doesn't matter how that looks. Actually, it's written down here. So in order to keep the energies not increasing infinitely, you rescale this down to by this factor lambda to -1/2. That makes the energies always be in the order of 1. And then you add the second term, and that's your Hn plus 1. Now the important thing is, if you go through this mapping, you might actually hope, or that's what you expect from these RG type of arguments, that when you go to infinity, there will be some fixed points. The mapping will lead to some fixed points. And you can infer the physics of these objects from the fixed points of the mapping. But the fixed points we already know. The fixed points of the single impurity Anderson model are V over or U going to V star equals 0 or U star, and U star can be anything. This is the free orbital fixed point. So the orbital is there, it doesn't couple, it's living happily alone on its own, and the band states are also happily living. So that's the free orbital regime. Then you can actually, with the fixed V, shift ED to 0 and U to 0, which then gives you some filling in between 0 and 1. This is the mixed valency fixed point. This object, J, this combination, you know, this is the end coupling, can actually explode to infinity, or V can explode to infinity. That's a strong coupling fixed point. Now those we know. We have discussed them before. This was a little bit non-trivial, but we know that if the parameters are chosen properly, this fixed point has to exist. So these are the 3 trivial fixed points. And then, of course, if you send epsilon d to infinity, then the orbit is empty. That's the empty orbital fixed point. So Antoine has already discussed all of those, actually. Nothing else happens here. So these are the 4 fixed points. Actually, this is not quite true. There might be actually non-trivial fixed point for special situations. Now, one special situation is if your band electron density of states or the hybridization function actually is not a constant, but does this type of power law decay at the Fermi energy. In that case, you encounter quantum phase transitions. And that leads to a non-trivial fixed point that is not on that list here. It's an immediate fixed point, and this one tells you there's a quantum phase transition. The same happens for the 2-channel Kondo model, meaning Kondo spin plus 2 electron degrees of freedom that can actually couple, where you have at a symmetric coupling, when both couplings are the same, you also have a non-trivial fixed point, a so-called 2-channel Kondo fixed point. And that was the picture in the very beginning where I talked about quantum phase transitions. That was this funny feature there. Okay, so actually this is what we know. Now the only thing we have to find out is how do the energy levels look like in this situation. So we have to basically diagonalize the objects in those different fixed points, and then eventually compare with our calculation. I mean, what you do is you solve this Hamiltonian sequence here, find a level structure, then compare with the level structure predicted by those fixed points, and then can decide, okay, that's that fixed point, that's that fixed point, that's that fixed point. It sounds trivial, it's not quite as trivial, but again, look at Krishnamurti's wonderful papers there, you really learn about that. Now there's one caveat at that point. As I told you, just go on adding. And as you know, this always increases the Hilbert space by a factor of 4 for the simple model, which means you have an exponential increase of the Hilbert space as you walk along, and only a few iterations are feasible, and you're quite sure never to reach the fixed point. So let's do it differently. And remember that these hopping guys decay exponentially as lambda squared lambda to the minus n. So they become smaller and smaller and smaller. That is, high and low energy states become effectively decoupled in the course of the iterations. And that means you can also only keep a manageable number of states per iteration because the other ones will never contribute to the low energy physics. So typically what you do is you start out with a certain number of states at iteration n, then you scale this up. Then at the next iteration you will get multiplied times 4 states, so 16 states here. But what you realize is that those states predominantly only modify those guys, and they never reach the physics of the four lowest energy states. So what you do is you just keep the four lowest energy states, and then in order to avoid growing ground state energy, you shift the ground state energy to 0, and end up with a set of 5 states again, which capture the essential low energy physics. So how many states you have to keep depends on the problem. So this is something you should vary in the course of a calculation to see whether you're really in business, because if you take not enough, then your system will simply slide away. And I'm probably way over time. 10 minutes? Because I want to show some pictures. Okay, so what you can actually do is you can also introduce symmetries that makes life easier. So implementation remarks, again, implies symmetries that gives you smaller matrices. You should parallelize the stuff. That is very easy because you have block Hamiltonians if you have symmetries, and then you can use OpenMP to parallelize. Runs on 8 processes with almost linear speed up. You should use BLAS-LAPAC for matrix operations. You should always do that. They're optimized, they're stable. And there are some tricks of the trade you can actually read off from the review article I just mentioned. Now, what are the physics? So let's start with a single purity Anderson model. That's our favorite toy model. And look at the renormalized or rescaled many particle energies as function of the NRG iteration n. That's shown here. And I picked out several quantum numbers. So Q is the charge quantum number. Q equals 0 means you have 1 electron per side everywhere. Q equal 1 is you have 1 additional. This is the spin. Okay, S equal 1/2 is clear what that means. And S equal 1 and 0 are the single and triplet respectively. The ground state is always kept at 0, so the ground state is the black line down here. And those are different states that are realized. And what you see here, if you go along these iterations, there are regions where things stay rather constant. So the levels don't change dramatically. Then there are regions where the crosses over into a different regime. Again, the levels stay more or less constant. And finally, at large energies, everything becomes constant, nothing changes anymore. So you can actually now find in this type of calculation 3 different, this was half filling. So this was the half filling case, particle symmetric model. So you find 3 distinct regimes. The first one is that. And if you now do what I told you before, diagonalize these different fixed points, you observe that this actually is the free orbital fixed point. So basically band electrons and local system do not talk to each other at all. This intermediate regime corresponds to the local moment, meaning here you have basically a spin sitting, and the spin is stable. But then if you go further on, you will end up in the strong coupling fixed point. And now the funny thing is, if you now make an analysis of this structure of levels here, you will find, like this one, that both this and this are actually Fermi liquids. But this Fermi liquid is different than that one. And the difference is very subtle, because what the Kondo effect does, I told you, is form a bound singlet. That is, you remove from your system one side. And since we have a finite discrete system, we have say an even number of sides here and an odd number of sides here. So the energy levels are different. They are shifted by some phase shift, and the phase shift is pi half. And beyond 70, nothing happens, so you're in the ground state. So that's an energy calculation. That's something you can do quite easily, and you can read off physics from that, knowing the structure of the fixed point Hamiltonian. So that tells you local moment crosses, free orbital crosses over at local moment, and eventually goes into strong coupling fixed point where the impurity spin is screened. So how about physical quantities? Well, what you can do is that each iteration corresponds to some energy or temperature scale, namely of the order of lambda to minus n half. And you simply evaluate expectation values along the path down the iteration. This is only meaningful for local observables, but that's okay. And one has to be a bit careful when one wants to calculate dynamics. So what's the result? So here's the thermodynamics for the impurity Anderson model. This is a small u. U over pi gamma naught. Remember, this was the magical factor. If this object is 1, things start to happen. It's 0.16. Calculation was done for a lambda of 2, which is reasonably close to 1. I kept 6,000 states. This is an overkill. Yeah, you can do the calculation with 500 states. They look very much the same. I did 79 sides, so I'm sure I'm the ground state. The whole thing took 600 seconds for that large number of states on my laptop here, doing this while it's Silke talk. using 4 CPUs as OpenMP, and I need 2 GB memory. No, memory is not a problem today. And what you see here is nothing. So this goes down. This is the impurity spin susceptibility, starts out with 1/8, no spin, goes down. Charge susceptibility goes down. The entropy starts out at log 4. Log 4 meaning you have 0, single occupied, doubly occupied state, crashes down to 0, and specific heat becomes maximal where this crushing down is fastest. And everything happens, if you now look here, this is T divided by gamma naught. Gamma naught is a fluctuation scale. All happens on that scale gamma naught. So this is nothing really fascinating. Yes?
So the previous discussion seems to suggest it was a ground state calculation, and now suddenly you're showing some temperature here. So could you comment on?
Oh, yes, that's what I said here. So each iteration corresponds to some temperature. And I mean, this is a subtle thing. So you should look up the corresponding articles. But you can actually say each iteration you have a high energy portion, which is killed by the Boltzmann factor, a low energy portion, which is not yet interesting. And then the thermodynamic quantities in this window will be actually dominated by this temperature. And then you can calculate temperature dependence. That's what. Now here is the same Anderson model. Now not with 0.16 but 16. So this is a very huge U. Again, similar thing. What you see here is quite different. Again, this is now the susceptibility times T, which is also called local moment. It starts out by 1/8 and then goes to 1/4 and stays there for a while, and then goes down to 0, and that's precisely moment formation, screening of the moment. So the charge doesn't do anything, it goes down. Here is the entropy. Entropy starts out at log 4, and then goes down when the moment starts to form to, okay, now my battery goes empty. Let's take that one. The battery is empty here too, which means, goes to log 2, which means we have a local moment, and then eventually screened down here as function of temperature, and that is the Kondo scale. This region here is the Kondo scale. And you see specific heat has 2 parts. One, again, where the charge fluctuation freezes out, and the second is where the spin is screened. Now, dynamic quantities. Since we have a discrete system, coarse graining and more or less broadening is necessary. A priori, we don't have energies only in the current window. That's what I told you. So every window defines an energy scale. And we have to patch them together somehow. There's one thing called complete Fock space that helps you doing this, or you can do interpolation. In any case, if you just look at the raw data, this is what I've shown here, you see for small iteration, you could envisage the Hubbard bands, but for high iterations, where you should be around the Fermi energy, this is what NRG thinks is the Kondo peak. Now, I wouldn't really identify any peak there, especially a very huge one. So it's 10 to the minus 24. So what you do then is you take these data, plug in some broadening, and it turns out this log Gaussian broadening is a viable idea with some broadening factor between 0.5 and 1. And now if you do the calculation for the small U case, where you expect nothing to happen, that's the result. Perturbation theory gives you the red curve, NRG gives you the blue curve, and you see they don't really match very nicely. The distribution of weight is not as good as it should be, and the height here is miserably wrong. So this will mean immediate trouble if you want to do that with DMFT, because if you plug this into a self-consistency loop, that will simply blow apart. Now, Ralph Buller had a wonderful idea, namely to start using equations of motion and actually define an improved estimator for the self-energy. This is this object here. You simply divide a very complicated but still local Green's function by the regular Green's function multiplied by u. That's the self-energy. You can define it that way. It's usually not usable, but in that case, it turns out it's the only way to really do calculations. And once you do that, calculate that object divided by the Green's function from energy, multiply by u, you get that curve here. So here is again, blue is energy, red is perturbation theory, and you see no difference. They're identical. This is not only because everything is 0. It's shown in the middle here, where you see the self-energy. Now the self-energy is not zero, it's small, but it's not zero. It has very characteristic structures, namely the real part shows a very nice linear region around the zero, and the imaginary part shows, if you're willing to buy me that, a parabolic part. So that's wonderful, you can use DMFT now. And that's what you do get when you take the other calculation with the 16. You get this wonderful nice resonance called Kondo resonance. These are the Hubbard bands. This is the Kondo or Aberconsu resonance. If you blow in, that takes this form. Well, can one say a little bit about the structure here? Yes, one can. You have a Lorentz form precisely at the spot here. Most of the cases down here, it's called Donner-Sandwich. This is an algebraic decay. And if you go further out, you will find logarithmic tails, which you would expect because you have these logarithmic divergences. And the self-energy in the middle, you have the square parabolic part, which deviates at some point. You have the linear region, and here the dashed line is the fit to linear region. And this is a 4.5 times 10 to the 7 times omega, which tells you you have a Fermi liquid with an effective mass of, well, 4.5 times 10 to the 7 plus 1. Yeah. Very big mass. So that's wonderful. Everything seems to be absolutely crazy. Now, we want to do finite temperatures because we want, for example, to see the antiferromagnetic transition. I'm done in a moment. The antiferromagnetic transition, and then we crank up temperature, and then this happens. So at a reasonable temperature, things still seem to look pretty nicely. Increasing temperature gives you this wonderful strange behavior. And if you go to very high temperature, now 20 gamma naught is basically melting the system, there's nothing left anymore from Hubbard bands or anything. And that's weird. And now you can say, okay, I'm not interested in these high temperatures, so let's stick to low ones and see what happens there. And lo and behold, even that is not that particularly funny, because you, instead of getting a single peak, which you expect more or less, you get this type of funny wiggle in there. And if you look at the self-energy, things become even more worrying, because first of all, you have this wiggle here, which tells you, because this is now a cusp going in the opposite direction, you wouldn't have a negative slope at the Fermi energy, you have positive slope. And the second thing, if you blow that up and then try to really fit Fermi liquid forms, this works wonderfully at zero temperature, but the expectation at finite temperature, first of all, would give you a parabolic maximum and not a parabolic minimum, and the shift is wrong. And that's what Antoine meant a few days ago, that calculating transport properties, you must get that shift right, otherwise you're in trouble. That tells you energy, quantitatively, at that point, for T equals 0, beautiful. For finite temperatures, careful. And the reason is that only the energy difference of one energy shell are relevant. So you have a reliable description of weights at T equals 0. But at T finite, you have to collect energy difference from all shells weighted with a proper Boltzmann weight. And there, you don't know what you're doing, basically. And even worse than that, because you have a finite temperature, everything below that temperature is obscure to energy. It doesn't know about it. So they have absolutely no information at all from low energies, which means everything at low energy is just a shrewd guess. Okay, that's it. Thanks for your attention. I'm sorry for overdrawing quarter of an hour, but I hope this was worth it. For those who are interested, one can do a little bit more. Up to 3 channels or 3 orbitals is possible for thermodynamics, but I don't want to trust dynamics in that case anymore.
So maybe we'll take 1 or 2 very quick questions and postpone it to the questions to the lunch, and Thomas is anyway around. So
yes, so just grab me and ask me. Yeah, people are hungry. I apologize for overdrawing. I didn't think that was so long, actually.